This is Lecture 9 for the St. Louis University course Quantitative Analysis, Applied Inferential Statistics. What we'll be talking about today are techniques for working with both string and factor variables, but really with a focus on factor variables in R. Working with factors in R necessitates at least understanding a bit about how missing data is stored in R, so we're going to be talking about that as well. There's two primary tidyverse packages that we're going to be using today. So the first is dplyr. Dplyr we've used before for wrangling data. The second package is forcats. Forcats is used specifically for working with factors, and very often we use forcats in the context of dplyr mutate calls. So we're actually going to be working with these packages together. Finally, we're going to be using janitor today to create frequency tables of the variables that we're working on cleaning. The data we use is going to come from test driver. We're going to be working with data that's stored in a table called GSS14 simple. This is the same GSS data that you've used for previous assignments, but these data have not been cleaned at all, so it's just the numeric values. We can go ahead and load the packages that we're going to be using today, and then load that data so we can take a look at how it is structured. If I load up the GSS data, you'll see that instead of seeing what the meaning are for various values, whether it's a 2 in income 16 or a 3, or a 1 for the race variable, or a 1 or a 2 for the sex variable, we just have the numeric values. Now, for continuous variables, this isn't a problem. We let the values speak for themselves. But for factor variables in particular, we want to know what the meaning of each of those values are. And it's easier if we can embed that meaning within the data table itself. And so that's going to be our goal for today. First thing we want to think about is how missing data appear here. We want to think about this because the GSS, like many data sets, assigns numeric values to things that we don't actually want to consider in our analyses. This could be categories like not applicable, don't know, no answer, or individuals who were never asked these questions to begin with. And if we create a frequency table for one variable, we'll pick the spouse's degree variable. We can see a full range of these. So for instance, a number -1 is assigned to 210 values in our data. These are values where there was no answer given. And they are coded as missing in the data set. We also have a value of 7. That 7 value for 1166 observations stands for not applicable. So these are likely individuals who were never married to begin with and therefore don't have a spouse's degree to report. We also have a value of 8 for 4 individuals. That 8 is assigned to don't know, and 9 is assigned to no answer. So the respondent chose not to answer the question at all. We don't want to include these in our analyses because any descriptive statistics run on this variable, say we calculate the mean, even if the mean is not a particularly relevant statistic for a categorical variable, -1, 7, 8, 9, they're all going to be included in those calculations. What we want to do instead is explicitly declare them as missing. And I have an example of this here where we use mutate from dplyr with an if-else statement to handle the following scenario. If spdeg, spouse's degree, is equal to -1, so that's this first part here. If spdeg is equal to -1, and remember the two equal signs, we want to recode those values from -1 to NA. NA is used in R to explicitly declare missing information as missing. Otherwise, we want to keep the existing values for spdeg. This is a really important step. If you put anything else in this false outcome of the if-else statement, it will change the actual structure of all the valid data that we really want to retain. And then I've included here a janitor table call again so we can see what the modified data looks like. We'll go ahead and execute that code chunk. And there we see we no longer have a -1 value for SPDEG. Instead, those 210 values have been declared as NA. We now have a column for both for percent and for valid percent. So the percentage includes the percent of cases that are missing. Valid percent does not factor that in. So this can be really helpful for describing our sample when we get to, say, a data and method section in a presentation or a paper. If we head over to the GSS data table again, go to the SPDEG column, we can see down here, the 22nd row, we have an example of a value that was -1 and now it is NA. And if I hold my mouse over, the tip shows text for null. So these are no longer included in any calculations that R is going to do that utilize this column. If else works very well when we have maybe one or even two conditions that we can string together with a logical operator. But when we want to make more deep changes across the entire variable, for instance, it's sometimes easier to use a dplyr function called case_when. Case_when is almost always used in the context of a mutate call, at least for our purposes. And it works well for when we have multiple missing categories or other categories that we want to modify. So what I have done here is taken the SPDEG variable that we've already cleaned once to make -1 missing. And I'm going to do two things. For the first 5 values of SPDEG, we are going to take the numeric values and assign them a character string that provides them more context in meaning. For the last 3 values of SPDEG, we are going to further declare those as missing. So like -1, these will no longer be factored into any descriptive statistics that are calculated using these data. So again, these are the responses for not applicable, don't know, and no answer. For all the explicit strings, we're going to provide a full text definition. And in parentheses, I'm going to include the original value. I find this really helpful. It helps me work back and forth between the original data set and the data that I have got cleaned up. So less than high school remains assigned as 0. And we're going to note here that that 0 was the original value used. A couple things to note about how I'm using case_when here. We're going to use a tilde to separate a test. That test is going to be a logical test. So if SPDEG is equal to 0, then assign it these values. If SPDEG is equal to 1, then assign it this value. Missingness is indicated not just by NA, but by NA_character_. I've noted below down here on point 3 that there are actually a number of specific NA values that case_when uses. NA alone, which we can use almost anywhere else to declare certain values missing. NA alone is reserved for logical variables. There are specific missing indicators for character, integer, and real data. The other change that I've made has to do with how we're going to display output. So in addition to my table call, I've added this adorn call. Adornments come with the janitor package, and they're designed to edit how that table call ultimately looks. This particular adornment, %formatting, will round all the percentages and add a % symbol so the table is easier to read. If I execute this code chunk, we see a couple of things. The NA category has grown considerably to include not just -1, but the original 7, 8, and 9 values. All of my labels have been assigned. You can see that here. And the % and valid % columns now include percentages as opposed to proportions. There's one problem with this, which is that because it's character data, all the value labels are displayed in alphabetical order, which doesn't make a lot of sense for these data because there is a kind of inherent order to them. Less than high school really should be the first listed value, then high school, then junior college, then bachelor, and then graduate. We can't influence this ordering with string data. That is what we use factor variables for. So in the case where we have a factor that we want to create, and it already has string definitions, we can use the factor relevel function from forcats to edit those values in terms of the order in which they appear. So we're going to do this in the context of a mutate function. We're going to set that spdeg variable equal to the outcome of factor relevel. Notice that I'm explicitly changing spdeg to a factor variable. It's an important step. And then I'm going to list each of the levels I want in the order that I want them to appear. So I want less than high school to be the lowest factor level, then high school, then junior college, then bachelor, then graduate. Again, we'll create a frequency table with the percentage adornment. Same frequencies, same percentage and valid percent values. All we've changed here is the order in which things appear. So factor variables allow us to override the default ordering that would be applied to a string variable. This is a bit of a complicated workflow, and we can simplify it in two ways. So one, we can use a pipeline to wrap a number of these steps together. And two, we can use factor recode to apply factor levels without first converting to a string variable. So this pipeline does two things. First, we take the modeg variable, so this is the mother's highest degree earned, and we're going to declare values 7 and 8 to be missing. Again, not applicable or don't know. Then we are going to use factor recode to assign particular value levels, in this case less than high school, to a given factor value. Notice that factor values are referred to as we would refer to strings, so we're going to wrap all those values in double quotes. And this will give us a very similar looking variable to the one up here in terms of order, in terms of formatting, just applied to the mother's highest degree earned instead of the spouse's highest degree earned, and we've done it in fewer steps. So there we have it. NA values have been properly declared. We have our value labels applied in the appropriate order. This is a much easier way to create those factors that we ultimately want from a numeric variable. Finally, we can also use factor recode to collapse different categories within a factor. So here we have less than high school, and more than high school as three new levels of a factor variable. We're going to set those equal to the original levels. So for every original level, we are going to define what we want the new level to be. Less than high school remains less than high school remains high school. All the other categories are set equal to more than high school. And that will give us the effect of creating a 3-level factor as opposed to a 5-level factor, where we have, again, less than high school, and more than high school for the mothers in the sample of the General Social Survey. So when do we use each of these functions? Well, we use if-else when we have a small number of edits. If I have to declare 1 or 2 values missing, I find it easiest to use if-else. Case when is helpful when I need to make a lot of changes. The one caveat with using case when is we need to specify changes for every value in a given variable. Factor relevel and factor recode, these are specific for factors, as opposed to if-else and case when that can be used on a variety of forms of data. Factor relevel is going to be for editing the order of already existing factors, and factor recode is going to be used for specifying values of new factors or changing values of an existing factor, as we did in the last example. Again, what we've covered today are techniques for working with factors, working with missing data. These will be useful as we approach the data cleaning for the final project and as we move forward with additional data cleaning for assignments for the remainder of the semester.